Hi everyone, my name is Shen Jin, and I am from lead center at Guangxi University of Science and Technology. It's my pleasure to present our joint work with Professor Wang today on an AIGC-driven framework for the structural and semantic assessment of complex information systems. First, why is matter? In the wave of digitalization, large-scale IT systems have become critical digital infrastructure for society. Establishing quantitative assessment framework is essential for robust operation and complex governance. However, these systems are difficult to assign regarding three main reasons. First, they are highly complex with many models, long interaction trains, multiple versions, and strong cross-department links. Second, the assessment is often inefficient because manual evaluation relies heavily on human experts' judgment, making it subjective, costly, and time-consuming. Third, governance needs are increasing as information systems must remain scalable, auditable, and suitable for cross-agency collaboration while helping decision-makers detect risks early. Therefore, the core issue to resolve is how to leverage AIGC to establish a quantitative and evidence-based framework. The presentation identifies three core technical challenges. First, system documents are highly heterogeneous, so they must be transported into machine-readable forms despite the semantic gaps and version differences. Second, the functional models are hard to inject because they are often described in non-standard and nested language. Third, system differences are multi-dimensional. So the framework must combine multiple feature and visual analysis to identify compatibility and upgrade risks. The framework addresses these challenges through a six-step assessment process. Step 1 is multi-source ingestion, which connect heterogeneous documents such as system requirements, technical specification, and operational flow charts. Step 2 is meta rejection, where AIGC convert unstructured text into standardized entities such as model names, version identifiers, functional tags, and ownership information. Step 3 is structural injection, which identifies key relationships among models, including dependencies, hierarchies, and process flows, so that static documents can be transformed into a functional map. Step 4 is topology modeling, which builds a hierarchical network of system functions. Step 5 is a quantitative assessment where structural and semantic metrics are compared to manual similarity, coverage, compatibility, and potential upgrade friction. Finally, Step 6 is governance output, which identifies friction point and provides warnings about upgrade risk. To human in the loop, control pointers have been embedded in the process. During metadata extraction, prompt tuning, and rule constraints have aligned AI output with domain policy and the stakeholder needs. During quantitative assessment, experts set threshold and verify edge cases to improve the reliability of the results. This hybrid approach helps resolve ambiguity in terminology and ensure that the system topology is both accuracy and useful for governance. The first methodology improvement focuses on business entity injection. AIGC is used as the core engine to process raw materials such as system requirement, technical specification, and operational flow charts. Instead of simply reading the text, it converts these documents to structured metadata, including notes, relationships, and properties. This improvement has three main functions. First, it can quickly identify implicit business entities that are often hidden in long and complex documents. Second, it standardized inconsistent terms from different departments or time periods into a unified metadata format. Third, it improves cross-system information alignment by identifying overlaps and conflicts across systems, helping achieve semantic consistencies in their operational logic. The second methodological improvement is topology graph generation. After entities are extracted, the framework builds functional topology network to represent system organization in a clear and more explainable way. This improvement has three main goals. First, it identified functional hierarchies by extracting subordinate invocation and the process flow relationship between models. Second, it improves structure extraction by recognizing what models do, what they depend on, and how they interact in workflows. Third, it resolves terms ambiguity, reducing connection errors caused by different terms referring to the same function. This improves the reliability of the topology model and make later similarity analysis more credible. The third methodological improvement is a multi-dimensional graph similarity analysis model. This is important because system similarity is not only semantic but also structural. A useful comparison must therefore consider both node level meaning and graph level structure. This model has three main components. First, semantic similarity calculation using a domain-specific BERT model to measure similarity between nodes and reduce problems caused by different expressions for similar functions. Second, structural similarity analysis uses graph editor distance and the maximum common subgraph method to identify deeper structural relation and distinguish cases where similar labels may represent different roles. Third, the framework combines semantic and structural results into a hybrid similarity score. This makes it possible to identify inheritance, adaptability, and upgrade friction more accurately. The framework produces three main outputs. First, it defines and measures evolutionary friction as the mismatch between high semantic relevance in new requirements and low structural similarity in the existing system. Second, it identifies typical friction scenarios such as functional fragmentation and topological rigidity, and links them to specific structural weaknesses. Third, it translates these results into visual risk dashboard, showing the distribution, concentration, and severity of break-question point. Together, this output makes the framework both an assessment tool and a decision support tool for governance and system evolution. To validate the framework, the presentation applies to this large-scale IT system in a certain region. The dataset includes 4 groups of baseline systems and 2 groups of upgraded architectures developed on the basis of existing function. The technical path is based on a functional topology similarity model that performs cross-system graph structure difference analysis. The main assessments dimensions include system coverage, compatibility, and functional enhancement. The newly upgraded information systems topology graph system D has a well-defined community structure and high connectivity. It shows stronger resilience as it can maintain a high level of connectivity even after targeted attacks on their nodes. Overall, the system demonstrates robustness and ability to withstand targeted destruction. This table compares system information system across 4 dimensions: architecture, scale, network coherence, resilience, and similarity to the reference system D. It shows that system A is the most similar to system D, while system C and E are highly divergent. System B have some structural similarities but remain non-homologous. Overall, the table helps us understand how these systems differ in structure, robustness, and alignment. In this figure, nodes and arrows in different colors are used to indicate corresponding similar functional nodes between reference system and other systems in different versions, where the gray part represents unmatched nodes or nodes with structural differences. Another major contribution of the framework is the construction of a structured evidence chain. First, it ensures traceability by linking each topology nodes to its original source document. Second, it improves explainability because similarity is measured through graph computation and explicit rules are than black box decisions. Third, it supports readability as the analysis code and rule matrix can be examined by third parties at any time. Together, these features make the framework both technically effective and institutional defensible. Beyond technical performance, the framework also creates important governance value. It improves access standardization, supports cross-agency collaboration, reduces upgrade risks, and strengthens the resilience of digital infrastructure. Overall, it's not only a technical tool, but also a governance tool for more accountable and sustainable digital transformation. This slide explains the synergy between AIGC and HITL in the framework. AIGC improves the efficiency by rapidly processing complex and heterogeneous documents and converting them into standardized functional maps. HITL ensure reliability of aligning AI outputs with domain policies, validating edge cases, and checking key thresholds. In short, AIGC provides scalability, while HITL provides control and trustworthiness. Together, they help balance efficiency and governance quality. This slide summarizes the benefits of AIGC-HITL integration in three dimensions: efficiency, accuracy, and governance. In efficiency, AIGC handles large-scale document processing where experts provide rules and constraints, reducing time and cost. In accuracy, AIGC performs semantic analysis and experts verify edge cases, improving risk identification. In governance, AIGC visualizes frequency pointers and system risk, where experts ensure policy alignment and support more transparent decision-making. This figure shows the dynamic balance between AIGC and HITL collaboration across three dimensions: efficiency, accuracy, and governance. It illustrates that when AIGC's large-scale processing capability is effectively combined with HITL's control and governance capacity, the framework can achieve better efficiency, higher accuracy, and stronger governance stability. The final part of the presentation discusses the future direction of the framework. It emphasized human-AI collaborative assessment, where AI provides scale and speed, and human experts provide judgment and accountability. The future roadmap includes three layers: multimodal data integration, automated governance alignment, and a lightweight continuous assessment platform. In the long run, the framework could evolve into a continuous governance infrastructure for monitoring, diagnosis, and decision support. That's the end of our presentation. Thank you for your attention.